Hello, my name is Jackson Deeroff, and today I'll be talking about gamma D crystallin. So, what is gamma D crystallin? It is a protein that is 173 residues long and has a molecular weight of about 20 kilodaltons. So, it's relatively small compared to things like Titus, for instance. But as you can see, there are two domains, an N terminus and C terminus, and they are homologous, so they are the same. Is that a Greek key on my screen? Oh, no, that's just a Greek key motif. So Greek key motif is characterized by a hairpin loop inside another. So as you can see here, there's a hairpin loop and then it wraps around to the subsequent beta sheet right here. And that's highlighted in red for you. There are two of these per domain, and they're responsible for maintaining the structural integrity of this protein. And it has a half-life of about 19 years, so it's pretty stable. The function of this protein, it's responsible for sustaining the refractive index within the eye. So that's about 1.3. And so that bounces or that refracts light onto our retina where we have our photoreceptors and make our images. And there is a critical balance of proteins and water that needs to be met to not only keep this refractive index, but also keep the grain boundary small enough so that it can remain translucent. So the significance of this, if these proteins aggregate, they start to cause blind spots, and this is known as cataracts. And so the only relief for this is surgical replacement of the lens. So they can either go in through the cornea and make small incisions to use an ultrasonic probe to break up that lens and put in a replacement, or they can make a bigger incision in the cornea to pull out the whole thing and then replace it. But that takes a little bit more time to recover from. And so how can this happen? So there is early onset cataract where there is an alanine substitution of leucine 145 and methionine 147. And this structural change causes it to dimerize very well, leading to cataracts. And then there's also age-related cataracts. So in our eye, there are certain protective mechanisms like vitamin E and C, among others, but they protect this from proteolytic cleavage at the highlighted in red, the aspartate and serine residues right there. And it can also cleave at the glycine and serine residues highlighted in blue. So once these are cleaved, these can aggregate very well, also leading to cataracts. So here are my references, and thank you for watching.